We have now studied the main mathematical methods for solving systems of linear equations. Next, let us see how these methods can be applied to economic and business problems. We begin with a multi-commodity market equilibrium model. Suppose there are n goods in the market. The important idea is that the price of one good may affect not only its own supply and demand, but also the supply and demand of other goods. For good I, the supply and demand quantity are written as a linear function of all prices. So, both supply and demand for one product may depend on the entire vector of market prices. This means that we are not considering each market separately. Instead, we analyze all markets together as an interconnected system. This structure allows us to formulate the market equilibrium problem as a system of linear equations in prices. Now let us use the supply and demand functions to determine the market equilibrium. For each good, the equilibrium condition is that quantity supplied equals quantity demanded. When we impose this condition for every good in the market, the supply and demand equations can be rearranged into a system of linear equations in the unknown prices. To simplify the notation, we define new coefficients as the differences between the corresponding supply and demand coefficients. The resulting system can then be solved for the prices P1, P2, Pn. These solutions are the equilibrium prices of the goods. Once the equilibrium prices are known, we substitute them back into either the supply functions or the demand functions to obtain the corresponding equilibrium quantities. So the main idea is straightforward. Set supply equal to demand. Form a linear system in prices. Solve for the equilibrium prices. And then determine the equilibrium quantities. Now we move to another important application, the input-output model. This model describes how different industries in an economy are connected through the flow of goods and services. In the table, each row represents the output of one industry and shows how that output is distributed to other industries as intermediate inputs, as well as to final demand. The term Xij represents the amount of output from industry I that is used by industry J. The term Bi represents the final demand for the output of industry I, while Xi represents its total output. So, for industry I, Xi is obtained by adding Xi1, Xi2, Xin, and then adding Bi. In other words, total output must be sufficient to satisfy both intermediate demand within the production system and final demand outside the system. This relationship provides the basic structure for building the input-output model in matrix form. To build the input-output model, we convert the transaction values Xij into technical coefficients. The coefficient Aij is defined as Xij divided by Xj. Here, Xij is the amount of output from industry I used by industry J, while Xj is the total output of industry J. Therefore, Aij tells us how much input from industry I is required to produce 1 unit of output in industry J. For example, if A12 equals 0.2, this means that producing 1 unit of output in industry 2 requires 0.2 units of input from industry 1. By calculating these coefficients for all industries, we obtain the technical coefficient matrix, denoted by A. This matrix summarizes the production relationships among all sectors in the economy. From the input-output table, we can write one total demand equation for each industry. For every industry, total output must cover two components: the amount required as intermediate input by all industries, and the corresponding final demand. Combining all of these equations gives a system of linear equations. This system can be written compactly in matrix form as x equals A times x plus b here. X is the vector of total outputs, A is the technical coefficient matrix, and b is the vector of final demands. By moving the term x to the left-hand side, we obtain I minus A multiplied by x equals b. This is the standard matrix form of the input-output model and will be used to determine the total output required from each industry. From the previous slide, we obtained the standard input-output equation, I minus A multiplied by x equals b here. I minus A is called the Leontief matrix. If the Leontief matrix is invertible, We can solve for the total output vector x by multiplying both sides by its inverse. This gives x equals the inverse of I minus a multiplied by b. So there are two common ways to determine the total output required by the economy. The first is to calculate the inverse of the Leontief matrix and apply the formula directly. The second is to solve the system I minus a multiplied by x equals b using one of the linear system methods introduced earlier, such as Gaussian elimination. In either case, the resulting vector x tells us the total output that each industry must produce to satisfy both intermediate demand and final demand. We now consider a simple macroeconomic equilibrium model without income tax. Assume a closed economy with no foreign trade. The economy is in equilibrium when national income is equal to total planned expenditure. Planned expenditure consists of household consumption C, investment I, and government expenditure G in this simple model. Investment I and government expenditure G are fixed, while consumption C is assumed to depend linearly on national income Y. Therefore, we have two economic relationships involving two unknown variables, national income Y and consumption C. By rearranging these relationships, the macroeconomic equilibrium problem becomes a system of two linear equations in Y and C. This is the main mathematical idea. Finding the equilibrium of the economy is equivalent to solving a linear system. We now extend the previous model by introducing an income tax. When income tax is present, households C do not consume based on total national income Y. Instead, consumption depends on disposable income ID, which is the income remaining after tax T. If the tax T is proportional to income Y with tax rate T, then disposable income is equal to 1 minus T, multiplied by Y. Therefore, the consumption function is modified accordingly. The important economic idea is that a higher tax rate reduces disposable income and therefore affects household consumption. However, from a mathematical point of view, the model is still based on linear relationships. The equilibrium condition itself does not change after introducing tax. National income must still equal total expenditure, while consumption now depends on after-tax income. Combining these two relationships gives a new system of two linear equations in the same unknown variables, Y and C. After rearranging the equations, we again obtain the standard form of a linear system. The key idea is that introducing income tax changes the coefficients of the model, but it does not change its mathematical structure. So, once again, the equilibrium can be found using the methods we have already studied for solving systems of linear equations. We now move to another important macroeconomic application. The IS-LM model. IS stands for investment saving, while LM stands for liquidity preference money supply. The model studies equilibrium in two markets at the same time. The IS equation represents equilibrium in the goods market, while the LM equation represents equilibrium in the money market. The two main unknown variables are national income, Y, and the interest rate, R. So the central mathematical idea of the IS-LM model is very simple. We have two equilibrium conditions and two unknown variables. Therefore, the IS and LM equations together form a system of two linear equations. Solving this system gives the equilibrium income and the equilibrium interest rate. Let us now see how the two equations are obtained. First, consider the goods market. Goods market equilibrium requires national income Y to equal total expenditure E. Consumption C depends on income Y, while investment I depends negatively on the interest rate R. After substituting these relationships into the equilibrium condition and rearranging, we obtain the IS equation, which is a linear equation in the two unknowns Y and R. Next, consider the money market. Money market equilibrium requires money supply to equal money demand. Money demand is assumed to increase with income and decrease with the interest rate. After imposing the equilibrium condition, we obtain the LM equation, which is also linear in Y and R. So, the important point is that both markets generate linear equations involving the same two unknown variables. We can now combine the IS and LM equations into one system. The first equation represents goods market equilibrium, and the second represents money market equilibrium. Because both equations involve the same two unknowns, y and r, the system can be written in matrix form. This has exactly the familiar structure. A times x equals b here. The unknown vector contains national income and the interest rate. Therefore, we can solve the as-LM model using the same methods developed earlier in this chapter, such as Gaussian elimination, inverse matrices, or Cramer's rule. The solution gives y** operator and r** operator, which simultaneously satisfy equilibrium in both markets. So the key idea is, two economic equilibrium conditions become a system of linear equations. And solving that system gives the overall macroeconomic equilibrium.